In the infinite silence between galaxies, something is tearing the universe apart, not with violence, but with cold, invisible fingers, stretching space-time like fabric on the edge of a blade. We've called it dark energy, a mysterious force accelerating the cosmos, rewriting the rules of gravity itself. But what if it's not a force at all? What if dark energy is a symptom, not a cause, a side effect of something stranger, deeper, maybe even alive? We thought we understood the void, but the void may be staring back, and it's not empty. Subscribe if you believe the universe still hides secrets. Join us as we peel back the veil on dark energy and uncover a possibility that could shake the foundations of reality itself. They were expecting to confirm the end of the universe. It was 1998. Two rival teams of astronomers, one led by Saul Perlmutter at Lawrence Berkeley National Laboratory, the other by Brian Schmidt and Adam Rees at the Australian National University, were racing to settle a cosmic debate. Is the universe coasting, or will gravity eventually halt its expansion? Their plan was simple in concept, audacious in execution. By studying distant type Ia supernova, the thermonuclear deaths of white dwarf stars, they could measure how fast the universe was expanding billions of years ago. These explosions, like cosmic lighthouses, always shined with nearly the same intrinsic brightness. If you know how bright something should be, and you know how dim it appears, you can calculate how far away it is. But what they found wasn't just unexpected, it was impossible. The light from these distant supernovae wasn't just redshifted, it was too faint, far too faint. That meant they were farther away than they should be. The implication, the universe wasn't just expanding, it was expanding faster now than it had been in the past. Something, some force was accelerating the entire cosmos in one stroke. Everything we thought we understood about gravity and cosmic evolution collapsed. This wasn't a gentle unfolding of space, it was a runaway, a cosmic jailbreak. The name given to this mystery was dark energy, a placeholder, a question mark dressed as an answer. But what if that's all it is? A label we slapped on our confusion, a polite way of saying we don't know. The assumption was that dark energy must be some kind of energy field, permeating space, pushing it outward, faster and faster, a pressure, a force. But there were whispers. Even then whispers that something about this didn't fit. What if dark energy wasn't a thing at all, but a symptom? What if it wasn't that space was expanding faster, but that time itself was shifting under our feet? Imagine standing on a train platform, watching a train leave. You measure its distance over time, assuming your clock ticks evenly. But what if it doesn't? What if your watch is changing speed without you knowing? The train appears to accelerate, but only because time betrayed you. Could something similar be happening in the universe? Some theorists have wondered if our measurements are skewed, not because space is stretching faster, but because time itself is stretching, warping, evolving. It's a radical idea, but radical ideas are exactly what science needs when the standard ones begin to fail. Saul himself, reflecting on the discovery, once said, "We had to be very careful not to believe our own assumptions. Because here's the thing, every measurement we make about the universe, redshift distance, expansion rate, relies on the assumption that time and light behave the same way they always have. But what if they don't? What if the speed of light was different in the early universe? What if gravity leaks into hidden dimensions, distorting our perspective? Or more hauntingly, what if we've misunderstood what expansion really is? It wouldn't be the first time our models led us astray. For centuries, we thought the planets danced in perfect circles until Kepler showed us they traced ellipses. We thought space was static until Hubble revealed its motion. We thought the universe was slowing down until 1998 shattered that belief. What else are we still wrong about? Some physicists argue that dark energy might be the result of a deep flaw in how we describe the vacuum of space. Others suggest it might not be a substance or field at all, but the result of unseen interactions between galaxies, or a kind of cosmic feedback loop baked into the fabric of spatemic. One thing is certain, this discovery cracked open a door, and what lies behind it remains hidden. Still, the question remains, if this expansion shouldn't exist, why does it, and what force, if any, is behind it? As we venture deeper into this mystery, we'll revisit one of the most brilliant minds in human history, a man who accidentally predicted dark energy long before it had a name and then dismissed it as a mistake. But what if Einstein's greatest blunder was no blunder at all? In 1917, Albert Einstein made a bold decision. Faced with the apparent stillness of the cosmos, a universe that, at the time, was assumed to be static and eternal, he altered the equations of general relativity, not because the math was wrong, but because the implications were too strange to stop the universe from collapsing under the weight of gravity. Einstein introduced a new term, the cosmological constant, or lambda. It was a repulsive force, a kind of anti-gravity, baked into the geometry of space itself. A mathematical ghost meant to keep the cosmos balanced, neither expanding nor contracting. But the universe had other plans. Just over a decade later, Edwin Hubble revealed that galaxies were rushing away from us in all directions. Space itself was stretching. The cosmos wasn't static. It was expanding. Embarrassed, Einstein reportedly called the cosmological constant his greatest blunder. And yet, nearly a century later, that same constant came roaring back, not as a blunder, but as a possible explanation for the accelerating universe. In the 1990s, when the supernova teams discovered the unexpected cosmic acceleration, lambda was dusted off and reintroduced. This time, not as a stabilizer, but as a driver of expansion, a subtle pressure embedded in the fabric of space-time, constant, omnipresent, and utterly mysterious. But what exactly is it? That's where things get strange. One interpretation is that the cosmological constant represents the vacuum energy, the energy of empty space. In quantum field theory, even a perfect vacuum is teeming with fluctuations. Particles pop into existence and vanish again in trillionths of a second. It's a seething sea of energy, what some physicists call the quantum foam. If we add up the energy from all these fluctuations, quantum mechanics gives us an answer, but that answer is a nightmare. The predicted vacuum energy is 10 times greater than the value we observe from dark energy. That's a number so large it defies comprehension. It's like saying the Empire State Building weighs 1 grain of sand, when in fact it should crush entire continents. This mismatch, the worst prediction in physics, has haunted scientists for decades. It's been called the vacuum catastrophe. So, what gives? Why does the math demand an absurdly large energy, while the universe whispers only a gentle push? Is something cancelling it out? Some theories propose that there may be a hidden symmetry, something deep in the laws of physics that we haven't yet uncovered, delicately tuning the vacuum to nearly zero. but not quite. Others suggest that the cosmological constant isn't a constant at all, but a dynamic field, changing slowly over time, a living equation. And then there are the radical interpretations. What if dark energy isn't a property of our universe, but a consequence of other universes? In the framework of string theory and the multiverse, every possible vacuum state could correspond to a different universe, each with its own physical laws. In this landscape, the vast majority of universes would be lifeless chaos, too fast, too slow, too violent for stars or atoms. Only a few rare regions, like ours, would have the just right amount of dark energy to allow galaxies, stars, and life. It's the anthropic principle taken to a cosmic scale, but many physicists find that unsatisfying. It doesn't explain why dark energy exists, only why we happen to be in a universe where it's survivable. That's not a reason, it's a rationalization. So the cosmological constant remains a ghost, elegant in theory, elusive in meaning. Even Einstein didn't know what it meant, only that the math demanded it. Today, the name lingers in his equations like a riddle he never solved. And yet, some physicists now wonder, what if he was right all along? What if the cosmological constant is the key? What if this tiny term in the equations of general relativity, a whisper at the edge of mathematics, is the most important clue in the universe? A silent fingerprint of a deeper reality. As one researcher put it, we may be looking at the handwriting of the cosmos and calling it nonsense simply because we don't yet understand the language. The ghost of Einstein's blunder walks with us still, but there's another shadow on the horizon, one that lurks not in equations, but in the void between galaxies. Because if the cosmological constant doesn't fully explain dark energy, maybe the answer isn't in what space is. Maybe it's in what space hides, what secrets lie in the black, cold distances no light has crossed. In the next chapter, we enter the void and discover that even nothingness may not be empty. Out in the vast, silent stretches between galaxies lies what we call voids. Cosmic deserts, so empty, they make interstellar space look crowded. But the deeper we look into these immense gulfs, the more it seems they may not be empty at all. Instead, they may be concealing the true nature of dark energy, or something even stranger. We tend to imagine the universe like a map of stars and galaxies scattered randomly, but that's not quite accurate. What astronomers have discovered is far more structured and far more eerie. Using deep sky surveys, like the Sloan Digital Sky Survey, scientists have mapped the cosmic web, a gigantic scaffolding of matter stretching across the observable universe. Galaxies don't just float in isolation. They thread together along filaments, long, bridge-like structures of dark matter and gas. These filaments connect at massive nodes, superclusters of galaxies, and in between them, voids, massive yawning regions where there is almost no matter. No galaxies, no stars, not even much gas. Some voids span hundreds of millions of light years. They're not just empty, they're hungry. They expand faster than the rest of space, pushing surrounding matter outward like a reverse gravity well. But here's the twist. These voids may not simply be passive bystanders in cosmic evolution. Some theorists suggest that voids amplify the effects of dark energy, accelerating the expansion of the universe more than dense regions do. In this interpretation, dark energy's influence may not be uniform. It may scale with emptiness. Imagine a sponge being pulled from all directions. In the denser parts, the fibers resist. But in the holes, in the air pockets, there's nothing to fight back. So the tension grows unchecked. That's what some believe is happening in the cosmic web. Voids are stretching faster because there's nothing left to hold them in place. In a 2016 study led by cosmologist Anna Sutter, simulations showed that voids could indeed evolve differently from denser regions, responding more sensitively to the effects of dark energy. The idea gained traction. Maybe we've been looking in the wrong places. Maybe we should have been staring into the dark enter pre-Anata region. A theoretical astrophysicist at Yale. Her work on gravitational lensing, how mass bends light, provides a new window into voids. Traditionally, lensing focuses on dense objects like galaxies and black holes, but Priya flipped the script. She asked, "Can emptiness bend light too?" The answer was astonishing. Yes, when light from distant galaxies passes near a cosmic void, it subtly changes. It stretches, twists, distorts, not from being pulled, but from being let go, like walking through a wind tunnel where the air pressure suddenly vanishes. These distortions, called weak lensing effects, are faint but measurable. And in 2023, data from the Dark Energy Survey began showing discrepancies between the expansion rates inferred from voids versus those from galaxy clusters. In simple terms, the universe may be expanding differently in different places. That shouldn't happen if dark energy is truly constant. But if it isn't, if it fluctuates based on the geometry of space itself, then our entire model needs rethinking. What if voids are not just regions of absence, but interdimensional membranes, areas where the fabric of space-time thins, or where our universe leaks into another? Some fringe models even suggest that voids could be portals, not in the science fiction sense, but as zones of extreme gravitational instability that could, under rare conditions, connect to other parts of the cosmos, or even to other universes. That may sound fantastical, but remember, black holes, once dismissed as absurd, are now photographed. The multiverse, once purely philosophical, is now seriously considered in string theory and inflationary cosmology. And if voids do have such hidden structure, then maybe dark energy isn't a force acting upon space. Maybe it's the expression of space reacting to its own topography. One provocative theory posits that dark energy may not even be a universal property, but a relational one, meaning it only emerges between things, in the emptiness between galaxies, not within them. It's not what space is, but what space does when it's alone. Pause for a moment and imagine that, a universe where the loneliness of space drives its acceleration. That's not just physics, that's poetry. But the implications go further. If dark energy is tied to the shape of space, to its curvature voids, filaments, then perhaps we've misread the map of the cosmos. Perhaps our measurements are biased, skewed by assuming uniformity where there is none. This opens a chilling possibility. What if the universe is expanding unevenly? And what would that mean for our future? In the next chapter, we'll explore an idea even more unsettling, that maybe it's not dark energy that's growing stronger, but gravity itself that's fading away. We trust gravity. We experience it every day. It keeps planets in orbit, stars bound in galaxies, and our feet firmly planted on Earth. It's the oldest force we've ever known, from apples falling in Newton's garden to Einstein's elegant warping of space-time. But what if gravity is lying to us? The idea seems absurd, yet some of the brightest minds in physics are now entertaining a possibility both profound and unsettling. What if gravity is not fundamental? What if it isn't a force at all, but an emergent phenomenon? To grasp this, picture a whirlpool in a stream. The whirlpool feels like a separate object, spinning with force. But it's not really there. It's just the result of water flowing around an obstacle. In the same way, some physicists now suggest that gravity might be a byproduct of deeper processes, not a standalone force. This radical idea gained momentum from the work of Dutch theoretical physicist Erik Verland. In 2010, he proposed something shocking. Gravity might emerge from entropy, the same concept that governs heat, disorder, and information. In Verland's model, space isn't just an empty stage. It's woven from information, and gravity arises from how information changes over time. The more disorder in a system, the more gravity seems to pull. It's not a force pulling you to the ground. It's the result of information trying to balance itself. That's hard to visualize. So let's simplify. Imagine space as a giant library. Every object, you, the moon, a black hole, is a book. As you move the books around, the shelves must reorganize themselves. Gravity, in this metaphor, is the sound of the shelves creaking and adjusting, not a force from the books themselves. Still with me? Now here's where things get truly cosmic. If gravity is emergent and not a real force, then our models that rely on gravity, including our explanation for dark energy, could be fundamentally flawed. In standard cosmology, dark energy is invoked to explain why gravity isn't slowing the universe down. But what if it's not that dark energy is accelerating space, but that gravity is weakening over large scales? Verland's emergent gravity model predicts just that. On short distances, like solar systems, gravity behaves as expected. But over cosmic distances, its grip loosens. Galaxies drift faster, apart not because something is pushing them, but because the invisible scaffolding of gravity simply isn't there. In 2016, Verland published a paper that shook the physics world. Using his model, he derived galaxy rotation curves, the very curves that originally suggested the existence of dark matter, without invoking dark matter at all. No invisible particles, just entropy and emergent geometry. The idea spread like wildfire. Some called it revolutionary. Others, dangerous. Could dark matter and dark energy both be illusions, symptoms of gravity not behaving as we thought? Observational evidence remains inconclusive. Some surveys of galactic motion match Verland's predictions, others don't. But the very fact that these models can make predictions without relying on unknown particles or exotic fields is a testament to their power. But it also opens a disturbing door, because if gravity isn't real, then neither is space-time, at least. Not in the way we imagine it. In some emergent models, space-time is a hologram, a projection of lower dimensional information, like a 3D movie projected from a 2D film strip. Our universe may be the visible layer of something deeper, more abstract, perhaps even non-local. In this framework, dark energy isn't a force. It's the manifestation of the hologram's tension, the stretch marks of space-time as it emerges from deeper rules we can't yet see. Let that settle for a moment. Everything you've ever known, light, time, distance, gravity, might not be fundamental. They might be side effects. And if that's true, then our attempt to find dark energy may be like trying to bottle the wind, without realizing it's the trees that make it sing. But there's another twist. If gravity emerges from entropy, and entropy is a measure of information, then perhaps consciousness, the very act of observation, plays a role in how reality takes shape. Could awareness itself influence space-time? That's a question we'll come back to later. But first, we must descend deeper, beyond the emergent, into the quantum dot, because, at the smallest scales imaginable, space doesn't stretch, it flickers, and there, in the foam of the vacuum, a new picture of dark energy begins to emerge. At first glance, the vacuum seems like nothing, a perfect, silent emptiness between particles. But zoom in far enough, far beyond the reach of any microscope, and the vacuum reveals its true nature, a violent, restless storm of fluctuations. This is quantum foam, and some believe it holds the secret to dark energy, and perhaps even to the architecture of reality itself. The idea of quantum foam dates back to physicist John Wheeler, who imagined that at the Planck scale, a mind-shattering 10 to 35 meters, space-time isn't smooth and continuous, but chaotic and bubbly. Like the surface of a stormy ocean viewed from above, it appears flat, but up close, it's seething with activity. Particles wink in and out of existence. Virtual particles are born from borrowed energy, live brief ghost lives, and vanish again, allowed by the strange permissions of quantum uncertainty. Even in perfect nothingness, energy is never zero. The vacuum is not empty, it's alive. Now imagine that each of these tiny flickering fluctuations contributes a minuscule amount of energy to space. One particle, insignificant. A trillion, still trivial. But across the vast, unthinkably large canvas of the universe, that's where the paradox begins. If you sum up the energy of all these fluctuations using quantum field theory, the total vacuum energy is enormous, minus 120 orders of magnitude higher than what we observe as dark energy. This discrepancy is so vast, it's been called the worst theoretical prediction in the history of physics. But what if we've misunderstood the vacuum? Some physicists believe that this quantum foam isn't just generating energy, it's generating geometry. In other words, space-time itself might emerge from the entanglement of quantum bits at the smallest scales. This leads us to a radical idea, known as the holographic principle. Born from the strange thermodynamics of black holes, the holographic principle proposes that the entire three-dimensional universe may be described by information encoded on a distant two-dimensional surface. Much like a hologram, you see the depth, you feel the space, but it's all projected from a lower dimensional source. One of the key insights came from Juan Maldacena, whose 1997 model of a DSCFT correspondence revealed a precise mathematical relationship between a gravitational universe and a quantum field on its boundary. In essence, gravity and space-time can emerge from entanglement, from pure quantum information. So how does this connect to dark energy? Some theorists propose that the mysterious force driving the universe's expansion isn't a force at all, but a feature of the hologram itself. Like light bending through an imperfect lens, the acceleration of the cosmos might be the distortion we perceive when reality is projected from a deeper informational layer. In this view, dark energy is not something we can detect directly. It's a shadow, the result of the limitations of our perception, the shimmer on the holographic screen, and the deeper truth might be hidden beyond the boundary of what we can ever observe. But that raises an unsettling question. If we are living in a hologram, then what are we? Are our thoughts, our lives, our memories just emergent properties of encoded data? Is consciousness itself a projection? Some physicists and philosophers suggest this may not be far from the truth. The boundaries between information, physics, and experience are starting to blur. In fact, Some researchers now describe the universe not as matter in motion, but as information processing itself. The cosmos as a quantum computer. Even time may be emergent, a sequence of causal relationships encoded across a deeper grid. And if time is emergent and space is emergent, then dark energy, that strange driver of cosmic acceleration, might be nothing more than the pressure exerted by information trying to arrange itself. Still, the mystery remains. If the universe is a hologram projected from deeper rules, who or what set those rules? Could they have arisen naturally, like mathematical inevitabilities, or were they written, designed? If dark energy is a property of the holographic projection, then perhaps it is not a force to be understood, but a clue, a signature, something pointing us beyond the veil. And that brings us back to the foam. The jittery, chaotic nature of quantum foam might not be random at all, but instead the canvas from which reality is painted, and the shimmering acceleration of space, a side effect of the projection's depth. We are used to thinking of the universe as what we see, but increasingly physicists are suggesting that what we don't see, the invisible scaffolding of information, the structure beneath the surface, may be what truly defines reality. And if that's true, then dark energy is not an enemy to solve, but a pathway to follow. But there's another path, one darker, more existential. Because what if the vacuum we live in is unstable? What if this universe, this elegant projection of space and light, is doomed to collapse into something else? Next, we explore the terrifying hypothesis that we may be living in a false vacuum, and dark energy is the ticking clock above the trapdoor. Imagine waking up one morning to find that the laws of physics have changed. Atoms no longer hold, light no longer moves. Reality, as you know it, collapses, not with an explosion, but with silence, sudden, total, and irreversible. This is not science fiction. This is the false vacuum hypothesis, one of the most haunting ideas in modern physics. And if it's true, then dark energy might not be a force, but a warning. To understand this, we first need to talk about vacuum states. In quantum field theory, what we think of as empty space can exist in multiple configurations, each with different energy levels. The lowest possible energy state is called the true vacuum, the most stable form of nothingness. But there can be local minimums, valleys that feel stable, but aren't the deepest. Picture a marble resting in a dent at the top of a hill. It seems stable. It's not moving, but a strong enough jolt, or even quantum randomness, could knock it free. And once it starts rolling, it doesn't stop, until it falls into the deepest valley. That's what physicists fear. We may be in a false vacuum, a precarious, high-energy version of space that only feels stable. And dark energy, it might be the tension, the quiet stress of this false state, a trembling before collapse. What makes this theory especially chilling is how it ties into the Higgs field, the field responsible for giving particles their mass. When the Higgs boson was discovered at CERN's Large Hadron Collider in 2012, its mass was measured at around 125 gigaelectron volts. That mass, when plugged into our models, places us worryingly close to conditions that suggest our vacuum may not be the true one. This isn't fringe speculation. In 2013, a paper by physicists Joseph Liken and Alessandro Strumia concluded that based on current data, the universe lies in what they called a metastable vacuum, a false vacuum that could in theory decay. If such a decay occurred, it would begin at a single point in space, A quantum fluctuation would cause the vacuum to tunnel into a lower state. This tiny pocket of new reality, governed by new physical laws, would expand outward at the speed of light, consuming everything, galaxies, stars, planets, all gone without warning. No light, no time to react, just erasure. Of course, this hasn't happened, so are we safe? Not necessarily. The fact that our universe has existed for 13.8 billion years doesn't prove stability. Quantum decay is random. It could take 1 trillion years, or it could happen tomorrow. What protects us, if anything, is not known. Some physicists speculate that unknown physics at high energies could lift the vacuum into stability. Others suggest that gravitational effects from inflation or dark energy itself might stabilize the vacuum in ways we don't yet understand. But here's the twist. Dark energy may be the key to understanding how close we are to the edge. If our universe is a false vacuum, then the energy we measure as dark energy might be the difference in energy between the false vacuum and the true one. That tiny energy gap, just enough to accelerate the universe, could be the tension of a universe out of place. It's like the hum of a guitar string stretched too tight, a sound you don't notice until it snaps. Some theorists even suggest that inflation, the rapid expansion of the early universe, was caused by a false vacuum decay, and that we may be living in the aftermath of one such transition. In that case, false vacuums aren't rare. They're how universes are born. Could this be a repeating cycle? Universes forming, expanding, collapsing, each one birthed from the death of the last. If so, then perhaps dark energy is not the end, but the midpoint, the breath before the plunge. It's not all doom. Understanding the false vacuum opens the door to exploring the landscape of possible universes, a concept championed by string theorists. In this vast multiverse, different vacua represent different realities, each with unique constants and laws. We may be just one bubble in a foamy sea of creation. And if our vacuum is false, that doesn't necessarily mean destruction. It may simply mean change, transition, transformation into something unrecognizable. The human mind recoils at this. We are wired to believe in permanence, but physics whispers a different truth. Nothing is truly stable, not even the vacuum we call home. So the next time you gaze at the stars, remember, the quiet isn't stillness. It's tension, and dark energy may be the echo of a cosmic imbalance, waiting to snap. But perhaps, before the vacuum falls, we'll catch another whisper, a new clue rising from the shadows, tiny, undetectable, perhaps older than the Big Bang itself. Next, we turn our attention to the axion, the elusive particle that may hold the key to both dark matter and dark energy. There are particles so faint, so ethereal, that if one passed through your body this very second, and trillions just did, you wouldn't feel a thing. They are ghosts of the quantum world, immune to the forces that bind atoms and hearts alike. But one of these ghosts, if it exists, may hold the secret to both the dark matter that anchors galaxies and the dark energy that tears them apart. It's called the axion, first proposed in the late 1970s by physicists Roberto Peccei and Helen Quinn. The axion wasn't created to explain cosmic acceleration. It was born out of a much smaller mystery, one buried in the equations of the strong nuclear force. According to theory, that force should have a symmetry-violating term, a kind of mathematical imbalance that should have left a visible mark on the universe. but we've never seen it. The universe, in this case, seemed too perfect. To fix the problem, Peck and Quinn proposed a mechanism that would cancel out the unwanted term. This mechanism predicted a new particle, incredibly light, electrically neutral, and nearly impossible to detect. That particle was later named the axion, after a popular laundry detergent, because it cleaned up the symmetry problem. But as theorists explored the axion's properties, they realized something remarkable. If axions exist, the universe should be flooded with them, not in violent collisions or blazing reactions, but as a gentle, ever-present field, a sea of invisible low-energy waves, washing through all of space like a forgotten cosmic current. This axion field wouldn't glow or scatter. It wouldn't heat or radiate, but its presence could affect the universe, subtly bending the behavior of particles, shifting the phases of fields, maybe even shaping the evolution of space-time itself. And here's where things get profound. Some physicists now believe that the axion field could play a dual role, acting as both dark matter and a component of dark energy. Think of the axion field as a cosmic hum, a background vibration that started early in the universe and has persisted ever since. Depending on its properties, it could clump into halos around galaxies, forming the invisible scaffolding we attribute to dark matter. But it could also, if tuned just right, create a kind of slow rolling pressure, a dynamic energy density that mimics dark energy. This idea is known as ultralight axion cosmology, and it's not just theory, it's gaining traction, especially as traditional dark matter candidates like WIMPs, weakly interacting massive particles, continue to elude detection. But the axion's ghost-like nature makes it incredibly hard to find. It doesn't interact via electromagnetism, so it doesn't shine. It doesn't collide in the way normal particles do. So, how do we find it? In a lab deep beneath an Italian mountain, shielded from radiation and cosmic noise, a team of scientists is listening, not with ears, but with resonant cavities cooled near absolute zero. This is the ADMX experiment, the axion dark matter experiment. They are attempting to detect axions by converting them into photons, tiny flashes of light using incredibly strong magnetic fields. If the axion exists, and if it passes through the cavity at just the right frequency, it might trigger a whisper of light, just enough to say, "I'm here." So far, no confirmed signal, but the search continues, and new experiments are coming online, including Casper, Haystack, and MATS, each designed to listen in different ranges, scan deeper, tune finer. What excites many physicists is that axions, if they exist, could also explain why the universe's vacuum energy is so small, the very mystery behind the cosmological constant. Some models suggest that axions can naturally relax the vacuum, balancing it through their dynamics. Instead of a fixed energy density, the universe would have a self-adjusting field, a cosmic thermostat. And then there's the mystery of where axions come from. Some theorists believe axions may not be just another particle, but a fundamental feature of high-dimensional string theory. In this view, every extra curled-up dimension in the universe generates axion-like fields. There could be hundreds of them, each with slightly different properties, each whispering a different story about what space is. If that's true, then the axion isn't just a particle. It's a portal, a messenger from realms we cannot yet see, and perhaps from times we cannot yet imagine. Some cosmologists speculate that axions may have formed before the Big Bang, relics of a previous epoch, vibrating through the phase transition that gave birth to our cosmos. If so, the axion field would be older than time itself, an echo of a universe that came before, guiding the one that came after. And what if this hum, this silent, vibrating field, is the very thing we've mistaken for dark energy? A subtle imbalance, a cosmic rhythm always there, just beneath the noise. If we could tune ourselves to that frequency, what would we hear? As the search continues, one thing is clear: the axion may be the softest voice in the universe, but it could carry the loudest truth. And yet, some believe we're not dealing with a soft whisper, but a scream we haven't recognized, because there's a model even more terrifying than any particle field, one where dark energy doesn't stay constant, but grows. And if it keeps growing, it doesn't end with silence. It ends with the universe ripped apart. The universe is expanding, that much we know, but the nature of this expansion, why it's accelerating, and how fast it's changing, holds a terrifying possibility. One that ends not in fire, not in ice, but in tearing. It's called phantom energy, a hypothetical form of dark energy that doesn't just push the universe outward, but does so with growing, unstoppable force. If phantom energy exists, it won't merely stretch space. It will shred reality, atom by atom, star by star, until nothing is left but silence. To understand phantom energy, we need to revisit a key concept in cosmology, the equation of state. This describes the relationship between pressure and energy, density in the universe. Regular matter has positive pressure. Dark energy, at least as we understand it, has negative pressure, which causes expansion. But there's a threshold. If the equation of state parameter, W, is exactly -1, we're dealing with a cosmological constant, a fixed, unchanging dark energy. If it's greater than -1, dark energy is dynamic but tame. But if W dips below -1, we enter the realm of phantom energy. This is where things spiral in a phantom energy-dominated universe. Expansion accelerates so violently that no force, not gravity, not electromagnetism, not even the strong nuclear force can resist it. The more the universe expands, the faster it expands. And as it accelerates, the very fabric of space becomes unstable. This leads to what physicists call the Big Rip. The term was coined in the early 2000s by theoretical physicist Robert Caldwell and his colleagues. They modeled a universe where phantom energy ruled and calculated a step-by-step timeline for the end. Here's how it plays out. First, galaxies would drift apart. No more galactic clusters. No more Milky Way Andromeda merger. Then, stars within galaxies would tear from their orbits. The solar system would unravel about 60 million years before the end. The Earth would be pulled away from the Sun. A few months before the Big Rip, the planet itself would disintegrate, its structure torn apart by the growing tension of space. Moments before the end, even atoms would come undone, and then, just like that, space-time itself, the lattice on which existence is built, would rip. Everything would end, not with a bang, but with a fracture. No signal could escape. No information could survive. Even time would lose meaning, caught in a geometric scream. It sounds like fantasy, but the math is sound if phantom energy is real. So, is it observations from the Planck satellite, the Dark Energy Survey, and WMAP all suggest that the equation of state is close to -1, not below it, not above it, but tantalizingly near. Still, the margin of error is large enough to keep the door open, and some studies, like a 2015 analysis of supernova data from the Supernova Legacy Survey hinted that W might be slightly less than -1, not conclusively, but enough to raise eyebrows. Then, in 2021, a paper led by cosmologist Valerio Mara suggested a time-evolving model of dark energy, one that starts near -1, but dips lower in the far future. This wouldn't just imply phantom energy, it would mean the Big Rip is already on the calendar. But when, depending on the parameters, it could be tens of billions of years from now, or, in extreme scenarios, just a few. The idea is controversial. Some physicists argue that phantom energy violates basic principles, such as the null energy condition, and would require exotic physics, perhaps even negative mass or energy borrowed from quantum fluctuations. But if the universe allows it, nature may not care whether we're comfortable with the math. Here's where it gets existential. In most end-of-universe scenarios, heat death, big crunch, there's a slow fade, a final moment when life flickers out. But the Big Rip allows no escape. No corner of space-time remains. No remnant survives. Not even the laws of physics. Some theorists speculate that the Big Rip could create a kind of boundary, a rupture, beyond which a new universe might emerge, like a cosmic reboot. Others believe it would be the final curtain. And what would it feel like? We wouldn't know. The last few seconds before the rip would pass in an instant. One moment we'd be, and the next we wouldn't. There's something uniquely horrifying about that, but also something poetic, because phantom energy forces us to confront the rawest version of cosmic impermanence. It's not just stars that die, the rules themselves die. And if dark energy is slowly evolving toward this phantom state, then every expansion we measure, every distant galaxy drifting away, could be a heartbeat in the countdown. Still, not all physicists are convinced. Many still favor a cosmological constant. Others suggest that dark energy may fluctuate, but never cross the -1 threshold. Yet the uncertainty is the point. We don't know. We can't know, not yet. So we watch, we measure, and we imagine. But in that uncertainty lies possibility, because maybe, just maybe, this escalating expansion isn't natural at all. Maybe it's not physics, but code, and if that's true, then dark energy may not be a feature of reality. It may be a glitch in a cosmic program. What if the stars above aren't stars at all, but pixels? What if the blackness between galaxies isn't infinite void, but unrendered space? What if the expansion of the universe isn't a force of nature, but a computational function? These aren't questions from science fiction anymore. Increasingly, serious scientists and philosophers are asking, are we living in a simulation? And if we are, could dark energy be the glitch that gives it away? The simulation hypothesis, popularized by philosopher Nick Bostrom in the early 2000s, argues that a sufficiently advanced civilization, capable of enormous computing power, might simulate entire universes, including conscious beings. If that's possible, and if such simulations are numerous, then statistically, we are more likely to be simulated than not. At first, this sounds like an abstract thought experiment, clever, but detached from real physics. But dark energy changes that, because in recent years, cosmologists have noticed something strange. The expansion of the universe behaves in ways that feel too smooth, too elegant, too perfectly tuned. It's as if the fabric of space is stretching, not from intrinsic energy, but from boundary constraints, like a map that only loads when you walk to the edge. This isn't just metaphor. In computer simulations, especially video games and 3D environments, programmers use something called lazy loading. A world is too complex to render all at once, so only the parts a user can see or interact with are simulated. Everything else stays dormant, uncomputed. Now imagine a universe that works the same way as we observe more distant galaxies. The simulation needs to create more space, more data. The act of observation stretches the map. In this view, dark energy isn't accelerating the universe. The rendering engine is. Some theoretical physicists are starting to wonder if this analogy holds deeper meaning. In 2020, a paper from Melvin Vobson proposed that information is not just an abstract concept, but a physical building block, a quantifiable component of mass and energy. This aligns with the controversial but growing idea that reality is made of information, not particles. If that's true, then perhaps dark energy is the energetic cost of processing cosmic data, the system-wide overhead required to simulate an expanding reality. We can even ask, what is the cosmological constant in a simulation? It might be the default setting, the background computational load necessary to sustain space-time at rest. But as observers, intelligent agents, begin interacting with the system, the processing demand increases. To compensate, the system expands space-time itself, reducing entropy density, maintaining balance. This theory finds eerie support in the observer effect from quantum mechanics. At small scales, particles don't have definite properties until they're observed. This isn't just weird, it's computationally efficient. Why simulate every particle's exact location if no one is looking? Now zoom out. What if this observer-dependent reality applies at cosmic scales too? Could galaxies only exist where we look? Could dark energy be a side effect of measurement? And if so, who or what programmed this? Enter the architect problem. A question that's both philosophical and scientific. If our universe is a simulation, does it have creators? Are we the experiment or the simulation's own emergent intelligence? Elon Musk, echoing Bostrom, once said, "There's a 1 in billions chance we're living in base reality." He's not alone. Physicist David Chalmers, MIT's Seth Lloyd, and even Neil deGrasse Tyson have all publicly entertained the idea. But can we prove it? Some researchers have proposed tests, like looking for pixelation in space-time, searching for irregularities in high-energy cosmic rays, or detecting anomalies in the cosmic microwave background, CMB, that resemble data compression artifacts. So far, the results are inconclusive, but tantalizing. In 2017, a team at Oxford analyzed cosmic data and found that if the universe were a simulation, its expansion pattern would mirror the resource scaling of a massive computer system under increasing load. That's exactly what phantom energy seems to do. But here's the deepest question of all. If the simulation hypothesis is true, does it change anything? Maybe not. If this is our universe simulated or not, it feels real. We think, we dream, we wonder. Our experiences are meaningful, whether or not they're computed. But there's a paradox. If dark energy is a programming artifact, if the expansion of space is the system's way of managing computational efficiency, then we may be approaching a limit, a processing threshold, a wall beyond which the simulation cannot expand without degrading. That would mean the observable universe is not infinite. It has an edge, a boundary, and perhaps, if we push far enough, we'll find it. Or maybe, just maybe, we already have. Because Some strange observations at the limits of the observable cosmos. Unexplained cold spots. Asymmetries in the CMB may be signatures, compression glitches, rendering seams, debug code. And if that's the case, then dark energy is not just a clue. It's a signature, a watermark on the simulation. But whether simulated or not, this universe follows rules. Rules that evolve, adapt, and obey deep laws of balance and disorder. And that brings us to the next puzzle. What if dark energy is just a byproduct of the universe organizing itself? A consequence of entropy, not intent. Everything decays, everything drifts toward disorder. From broken cups to dying stars, the universe trends in one direction, entropy. It's not chaos for chaos's sake. It's the most fundamental law of thermodynamics. And what if this cosmic drift toward disorder is the real engine behind dark energy? Entropy is often misunderstood. It's not destruction, it's information loss. The number of ways a system can be arranged without changing its overall appearance. A shuffled deck of cards has higher entropy than a neatly ordered one, simply because there are more ways to be disordered than ordered. Apply this to the cosmos, and the implications are staggering. The second law of thermodynamics tells us entropy always increases. From the moment of the Big Bang, a hot, dense, low-entropy state, the universe has been unraveling, expanding, cooling, spreading its energy, thin across time and space. But here's the twist. Some physicists believe this unraveling is what drives the expansion of space, that dark energy isn't a separate force at all, but the geometric effect of entropy reaching for equilibrium. Imagine the universe as a balloon filled with hot gas. As the particles spread out to maximize their disorder, the balloon expands. But this isn't just an analogy. It's a direct parallel to some models of cosmology where space-time itself stretches in response to increasing entropy, the idea gained traction in 2011 with a controversial proposal from theoretical physicist Eric Verland. We met Verland before in Emergent Gravity, but this time his work dove into entropy's relationship with information and how both might shape the fabric of the cosmos. In Verland's entropic gravity model, the force we perceive as gravity arises from the universe's tendency to maximize entropy. Masses curve space not because of some invisible force pulling them together, but because such configurations maximize informational disorder. Space bends to obey entropy. Now flip that logic. If gravity emerges from entropy gradients, then the acceleration of space, what we call dark energy, could be the cosmos equalizing itself on a grand scale. In other words, the universe may be expanding not because of a mysterious pressure, but because it's computationally efficient to do so. The bigger the universe gets, the more microstates become possible, the more ways it can arrange its energy without collapsing. Expansion becomes a thermodynamic necessity, not a mystery. But how does this hold up observationally? In 2020, a team led by physicist Thanu Padmanabhan explored a variation of this idea. They proposed that the expansion of the universe is directly linked to a mismatch between degrees of freedom on the surface of space and those inside it. This is a concept borrowed from holography, the idea that the information in a volume of space can be described by data encoded on its boundary, when the surface entropy and bulk entropy are out of balance. Space expands to resolve the discrepancy. That expansion, steady, smooth, and accelerating, looks exactly like dark energy. It's elegant, minimal, no exotic particles, no unknown fields. just entropy, trying to balance the cosmic books. And it may help explain the otherwise baffling coincidence problem. The question of why dark energy only became dominant in the relatively recent universe, long after matter formed galaxies. In entropic models, this isn't coincidence. It's timing, as structures like stars and black holes form, increasing entropy locally. The global entropy budget demands compensation. Expansion picks up speed. The universe adjusts. It's like a thermostat in a self-regulating system. Every change inside triggers a change in the container. But there's a dark undercurrent to this view. If the universe is driven by entropy, and entropy only increases, then the final destination is heat death, a cold, dark, motionless eternity, where all usable energy is spent, a perfect, featureless equilibrium. No stars, no movement, no life. In this scenario, dark energy isn't a threat. It's a promise, a whisper from the future, telling us how this ends. Expansion accelerates, not out of malice, but as the ultimate expression of balance. The more we live, burn, radiate, evolve, the faster the cosmos stretches to dilute us into equilibrium. And that's the paradox. The more complex we become, the faster we vanish. But some see hope in the mathematics, because entropy, while destructive, is also creative. It's what drives chemical reactions, births, stars, and fuels evolution. Disorder allows room for change, and change gives rise to complexity. In that complexity, intelligence. In intelligence, reflection. So perhaps dark energy, entropic, emergent, inevitable, is not the death knell of cosmic purpose. Perhaps it's the mechanism that makes purpose possible. But others see a darker alternative. What if dark energy isn't the universe's response to entropy, but its reaction to something beyond? What if it's not the expansion of disorder, but the imprint of another universe brushing up against our own? In the next chapter, we step beyond the edges of our cosmos and into the shadows of others. In the deepest black of space, where no starlight reaches, there is a cold spot, an anomaly, a region in the cosmic microwave background, the afterglow of the Big Bang that's just a little too empty, a little too smooth. It doesn't fit our models. It shouldn't be there, unless something else left its mark. What if the universe we see, our entire observable cosmos, is only a bubble in a far larger sea, a single pocket of reality adrift in a multiverse? And what if dark energy isn't just a property of our universe, but the bruise left behind by a collision with another? The idea may sound fantastical, but it emerges naturally from some of the most respected cosmological theories. During the first fraction of a second after the Big Bang, the universe underwent inflation, an unimaginably rapid expansion, but inflation, according to eternal inflation theory, never truly ends. Instead, it continues in pockets, spawning bubble universes like boiling water on a cosmic stove. Each bubble contains its own space-time, its own laws of physics, its own version of reality. Our universe is just one such bubble. The space between these bubbles, it expands forever, driven by a higher energy vacuum, the very same field that could explain dark energy. But here's the twist. If another bubble universe formed close enough, its expansion could intersect with ours. The collision would be catastrophic, but it would also leave a signature, a circular imprint, a gravitational shockwave, a cooling scar in the sky. Some scientists believe we may have already seen it. In 2007, physicist Laura Maseni-Houghton proposed that the CMB cold spot, a large, unusually cool region in the southern sky, could be the remnant of such a collision. Not a statistical fluke, but evidence of another universe pressing against our own. She wasn't alone. Later studies by NASA's WMAP and the Planck satellite confirmed the cold spot's existence. And while mainstream explanations point to a massive supervoid, a vast region of underdense space, that explanation feels incomplete. The void is too shallow. The temperature drop too sharp. Some researchers argue it can't be explained by any known local structure. So what's left? A cosmic bruise, a scar from a bubble we'll never see, but that shaped our destiny. If this is true, it suggests that dark energy might be a leftover effect from inflation's unfinished business, a residual tension between vacuum states. The slow, steady expansion we now observe could be the aftershock of multidimensional chaos. It also helps explain why the dark energy density is so small, not zero, but not vast. In a multiverse scenario, universes with too much dark energy expand so fast that galaxies never form. Universes with too little collapse before stars can ignite. We live in the rare middle, the Goldilocks zone of vacuum energy. But this raises the anthropic question: is our universe the way it is because it had to be, or because it's the only one where we could emerge to ask the question? It's a circular logic, and many scientists are uncomfortable with it. But in the absence of a better explanation, the multiverse provides a compelling and haunting frame. Some models go even further in brain cosmology. Inspired by string theory, our universe may be a three-dimensional membrane floating in a higher dimensional space. Other brains, other universes, could be just millimeters away, separated not by distance, but by dimension. If two brains collided in the distant past, it could have triggered the Big Bang itself. And residual forces between these brains could still be acting on our universe today, perhaps explaining dark energy not as an internal property, but an external pressure. In 2001, physicists Paul Steinhardt and Neil Turok developed a cyclic model based on this idea. Universes don't just expand and die, they bounce, collide, reboot. Each collision seeds a new Big Bang, and the cycle begins again. In that case, dark energy is the pulling tension between brains before the next collision, a cosmic inhale before the universe breathes out once more. Still, these ideas remain speculative. No telescope can peer into another universe. No signal can cross the boundary of space-time, but the clues are mounting. In addition to the cold spot, researchers have found anomalous flows, regions of space where galaxy clusters move together in strange, unexplained ways. Some call it the dark flow. It could be statistical noise, or it could be gravitational tugging from something beyond our observable edge. If we're being pulled or pressed from the outside, then dark energy is not a thing within us. It's a response to something outside us, a whisper through the wall, and maybe a message. Because if there are other universes, then perhaps their existence isn't silent. Perhaps they bleed into each other in subtle, encoded ways. Through gravity, through vacuum energy, through the shape of the void. And if that's true, then our universe, everything we know, may be just one sentence in a larger story. But there's another variable we haven't yet questioned. We've assumed the expansion is a function of space, but what if it's a function of time? We measure the universe by how fast it expands. We track galaxies, redshifts, and cosmic distances all tied to a single rhythm: time. But what if the universe isn't accelerating outward because space is stretching faster, but because time itself is slowing down? This is the provocative question behind the time variable hypothesis, a fringe yet fascinating idea that flips our perspective on dark energy. Rather than viewing acceleration as a change in how space behaves, it asks, what if it's our clocks that are changing? We assume time ticks at a constant rate everywhere in the cosmos, that a second is always a second. But time, according to Einstein's own theory of relativity, is not absolute. It bends under gravity, it dilates with speed, it warps near massive objects. So why should it remain fixed across the entire expanding universe? Here's the thought experiment. Imagine you're watching a movie on a projector, but slowly the projector itself begins to run more slowly. The movie on the screen appears to stretch, scenes take longer, movement looks slower, not because the film is changing, but because your reference frame is. Now apply that to the cosmos. If cosmic time, the fundamental clock of the universe, is gradually slowing relative to our measurements, then distant supernova would appear dimmer, not because they are farther away, but because the light reaching us has taken longer than expected. The whole illusion of acceleration could be an illusion of temporal drift. This concept was explored in depth by theoretical physicist José Novella, who in 2007 proposed a model in which no dark energy is needed at all. Instead, the acceleration we observe is a result of time flow. As time slows down across the cosmos, space appears to stretch faster, because we're measuring it with increasingly outdated clocks. The model is radical, but mathematically consistent, and it makes one profound claim. The universe's expansion might not be speeding up. We're just aging in a way we don't understand. To test this idea, we look to the cosmic microwave background, the afterglow of the Big Bang. It is a snapshot of a younger universe. If time flow is variable, it should leave imprints in how the early universe evolved. Tiny asymmetries, irregularities in redshift distributions, and subtle shifts in large-scale structure. Some researchers claim such anomalies exist. The Hubble tension, for example, the stubborn discrepancy between local and early universe measurements of cosmic expansion, might be explained if time flows differently now than it did then. Think about it. One method, based on nearby supernova, tells us the universe is expanding at about 73 kilometers per second MPC. Another, based on CMB observations, says 67 kilometers per second MPC. The difference has defied resolution for over a decade. If time itself is changing, slowing relative to our expectations, then both results could be right, from within their own temporal frames. But this raises a deeper question. What is time? Is it a dimension, like space, that stretches and bends? Or is it something else entirely, a process, a byproduct of entropy, or even a property of consciousness? Some physicists believe that time doesn't exist at the fundamental level, that the universe is, in its purest form, timeless, a static block in which past, present, and future all coexist. Our perception of time's flow would then be an emergent illusion, like heat from friction. If that's true, then changes in the rate of time might not be changes at all, just different perspectives within the block universe. Dark energy, under this lens, becomes a byproduct of perspective, a trick of the frame, not a real force. This model also dovetails with ideas from loop quantum gravity and causal set theory. where space-time is composed of discrete units, and time itself emerges as a kind of ordering principle. If the fundamental structure of time is granular, not smooth, then its flow could vary in ways we haven't yet imagined. But the implications are unnerving. If time is variable, then everything we've dated, from galaxy formation to the age of the universe, could be off. It may mean the cosmos is older or younger than we think. It may mean that cosmic acceleration isn't a sign of a dying universe, but a mirror of our deep misunderstanding of the flow of events. And if time is changing, could it stop? Could we approach a point where time freezes and all motion, all thought ceases? Or might time reverse, loop, fragment? No one knows. But one thing is certain: we've taken time for granted, treated it as a constant in equations, a backdrop to events. But maybe it's the main character. Maybe dark energy is not about space moving faster, but about time unraveling beneath us. Still, despite all this speculation, science must return to observation, and in the deserts of Chile, a telescope is preparing to look deeper than ever, not into space, but into what space is doing. High in the Atacama Desert of northern Chile, where the sky burns with stars and the air is still and bone dry, a new eye is about to open on the universe. The Verisi Rubin Observatory, nestled in the shadow of Cerro Pachin, is more than just a telescope. It is a time machine, a sentinel, a watchtower for the greatest cosmic mystery of our age, dark energy. When it becomes fully operational, this observatory will conduct the legacy survey of space and time, the LSST, over a decade. It will scan the entire southern sky every few nights, capturing motion, light curves, and redshifts for billions of celestial objects, galaxies, supernova, asteroids, quasars. It will collect more data than any optical survey in human history. But it isn't just about pictures, it's about patterns. Patterns that might reveal how the universe's expansion is changing, and whether dark energy is a static backdrop, or a dynamic, evolving presence. At the heart of this mission is Dr. Rachel Livermore, an astrophysicist who has spent years preparing for this moment. What we're looking for, she explains, is not a thing we can touch. It's not particles or waves. It's how the universe moves when we're not watching. The Rubin Observatory will detect thousands of Type Ia supernova, the same kind of stellar explosions that first revealed the accelerating universe in 1998. But this time, the sample size won't be a few dozen. It'll be hundreds of thousands. Enough to detect tiny deviations in redshift, to test whether dark energy has been constant over time, or if it's changing. If it's changing, we'll know. And everything we think we know about the fate of the cosmos will shift. The L will also map the phenomenon of weak gravitational lensing, the subtle distortion of light from distant galaxies, caused by the invisible mass it passes through. By analyzing these distortions, scientists can reconstruct the distribution of dark matter and, more importantly, how the geometry of space itself is bending over time. If dark energy is truly uniform, the lensing data should follow a predictable trend, but if there's variation, ripples, flows, clustering, it may reveal that dark energy isn't a smooth field. It might be lumpy, local, or even interacting with matter in ways we didn't expect. And here's where things get personal. For all its abstract grandeur, dark energy is a human story. A story of people often working in remote places, late into the night, chasing shadows with math and glass. People like Livermore, who remembers staying up during long Chilean nights, watching the test instruments on a cold monitor, waiting for the first photons to arrive. There's something about standing under that sky, she says. You feel how small you are, but also how connected. Because for all the complexity of dark energy, what we're really doing is measuring relationships between galaxies, between forces, between what we see and what must be there. Every observation is an act of trust in our instruments, our models, and ourselves. But the stakes are rising. In 2023, preliminary LSST data began trickling in. Nothing conclusive yet, but already whispers of statistical tension are emerging. Tiny mismatches between theory and reality. Some values drift above expectations, others dip below. No single anomaly is enough to declare a revolution, but collectively they form a pattern, a pressure building beneath the surface of certainty. As more data arrives, the scientific community braces, because it's possible, just possible, that what we call dark energy isn't just misunderstood. It might not exist at all. It might be a misreading of space, or time, or gravity, and if so, the Rubin Observatory could trigger what physicist Sean Carroll calls a paradigm collapse, the moment when the scaffolding of our cosmological model gives way, and we have to rebuild everything. There's fear in that, but also wonder, because we've been here before. In the early 1600s, astronomers stared through crude glass tubes and saw moons orbiting Jupiter, destroying the geocentric model. In 1919, an eclipse proved Einstein right, showing that light could bend and Newtonian gravity was incomplete. And in 1998, two rival teams looked at dying stars and realized the universe was flying apart. Now we look again, but this time not with hopeful ignorance. We know what we're searching for, and we know it might not make sense. Livermore pauses when asked about what she hopes to find. I don't want to confirm our theories, she says. I want to break them. That's when we learn the most. The Rubin Observatory is not just a telescope. It's a dare, a challenge hurled at the sky, asking, what else are you hiding? But even as we build these machines, these modern cathedrals to reason, the universe continues to confound us, because some of the most precise data we have doesn't fit. In the next chapter, we confront the growing mountain of contradictions, the cracks in our model that refuse to go away. The numbers don't lie, but maybe our assumptions do. Science thrives on numbers, patterns, consistency. For over a century, cosmology has relied on precise measurements to map the universe's evolution and, in turn, shape our understanding of forces like dark energy. But what happens when the numbers no longer agree? What if the data begins to fracture? This is the Hubble tension, one of the most persistent and unsettling problems in modern astrophysics. It's not a small disagreement. It's a fundamental crack between two ways of measuring the expansion rate of the universe. A crack that's widening, year by year, named after Edwin Hubble. The Hubble constant H describes how fast the universe is expanding at any given moment. The problem: different methods yield different values, and neither side seems to be wrong. Let's break it down. One method measures nearby supernova and Cepheid variable stars, standard candles whose brightness tells us their distance. From that, we determine how fast galaxies are receding. This approach, championed by Adam Rees and his SHOES team, gives a value of about 73 kilometers per second (MPC). That the other method looks to the cosmic microwave background, the frozen light from the early universe. by modeling how primordial fluctuations evolved into galaxies and clusters. Researchers, notably the Planck collaboration, derive a lower value, around 67 kilometers per second (mpc). The difference between these numbers isn't just noise, it's a 5 sigma discrepancy, statistically significant enough to suggest that something is fundamentally wrong with our understanding of the cosmos, and dark energy sits right in the crosshairs. If the universe's expansion isn't behaving the way our models predict, then our assumptions about dark energy, its density, its constancy, its role in cosmic acceleration might be off. The tension has prompted a wave of proposed explanations, each more exotic than the last. Some theorists suggest a form of early dark energy, a fleeting burst that occurred shortly after the Big Bang and altered the universe's expansion rate before settling down. In this model, dark energy is not constant, it's time-dependent, evolving in ways we haven't yet mapped. Others propose modifications to general relativity, itself tweaking the equations Einstein left us to allow for gravitational leakage, new scalar fields, or interactions with dark matter that distort the expansion curve. There are also radical ideas involving neutrinos, extra dimensions, or new fundamental forces that only become apparent on cosmic scales, but each theory comes with a cost. It must explain the Hubble tension without breaking everything else that already works. And that's the catch. Our current cosmological model, CDM, short for lambda, cold, dark matter, fits nearly all observed data incredibly well. The shape of the CMB, the distribution of galaxies, the success of Big Bang nucleosynthesis. It's one of the most successful models in science. But CDM requires dark energy to be constant, the lambda in its name, and assumes that the physics of expansion has stayed the same over time. The Hubble tension suggests otherwise. It suggests a dynamic component to dark energy, one that may have shifted in strength, or even character, since the early universe, and this isn't the only anomaly. Other tensions are emerging. Discrepancies in large-scale structure formation, conflicting measurements of galaxy clustering, hints that gravitational lensing is slightly weaker than predicted. Each on its own might be dismissed, but together they paint a picture of a model. Under stress, in 2022, a consortium of cosmologists released the Tensions in Cosmology report, a sobering, detailed review of the growing list of inconsistencies. Their conclusion: we are not yet in crisis, but the foundations are shaking. Some worry we're falling into a data-driven trap, constantly adjusting models to fit new observations, adding complexity without clarity. Others see this as the edge of discovery, the moment before a breakthrough. The truth is, we've been here before. In the late 19th century, physicists added epicycles to planetary motion to explain irregular orbits, until Einstein rewrote the rules with relativity. Today, we're adding new parameters, new fields, new energies, hoping something sticks. But maybe it's not the models that need tweaking. Maybe it's the questions. Are we assuming too much about the uniformity of the universe? About the constancy of time, space, light? Is dark energy truly a force? Or is it an artifact, a shadow of something deeper? And could it be that the missing piece isn't a particle or equation, but something more profound? Something tied not to space, but to consciousness itself? Because, in the quantum world, what we observe, and how we observe it, changes what is real. What if the same is true at the scale of galaxies? What if dark energy isn't out there, but partly a reflection of us? In the next chapter, we explore the most radical idea yet, that consciousness might not just observe the universe, it might shape it. There is a rule in quantum physics that defies common sense. Observation changes reality. In the double-slit experiment, particles behave like waves until you watch them. Then they choose a path. The universe seems to know when you're looking. For decades, this was considered a microscopic quirk, a curiosity confined to atoms and photons. But now, some scientists are asking a far bolder question. What if consciousness plays a role on a cosmic scale? And more provocatively, what if dark energy is not a force in the universe, but a reflection of the universe being observed? At first glance, this sounds like philosophy, not physics. But the lines are blurring. The fundamental nature of consciousness remains one of the greatest mysteries in science, and it sits uncomfortably alongside our equations. We can measure particles, we can model galaxies, but we cannot fully explain awareness. And yet awareness changes everything. In quantum mechanics, every system exists in a superposition, a cloud of possibilities, until an observation collapses it into a definite state. This collapse isn't just metaphorical, it's mathematically real, and no one knows what triggers it. Some interpretations, like Copenhagen, suggest measurement causes collapse. Others, like many worlds, say collapse never happens. All outcomes play out in parallel, but some physicists, like Roger Penrose, have proposed a more radical idea, that consciousness itself causes collapse. That there's something about awareness, not mechanical interaction, that selects outcomes and defines reality. If that's true on the quantum scale, could it apply to the cosmos? This is the foundation of the consciousness variable hypothesis. The idea that observation, intelligence, and awareness are not passive byproducts of the universe, but active components in its evolution and dark energy. It might be the large-scale response to the increasing information processing capacity of the universe itself. Let's step back. The universe has been expanding for 13.8 billion years. For most of that time, there were no stars, no planets, no life, just hydrogen and helium in a cooling fog. But somewhere along the way, complexity emerged. Biology, cognition, mathematics, language, science. Suddenly, the universe was looking at itself. And shortly after, within just the last sliver of cosmic time, the expansion of the universe began accelerating. Coincidence? Perhaps. But it invites a question rarely asked in cosmology. Does observation scale? In 2006, physicist John Wheeler, a key figure in quantum theory, proposed the concept of a participatory universe. We are not simply observers, he said. We are participators. In some strange sense, this is a universe that requires observers to bring it into being. Wheeler didn't mean we created the Big Bang. He meant that information and observation are woven into the fabric of reality, and perhaps, at some deep level, reality is incomplete without them. Recent work in quantum information theory supports this idea. The field views the universe as a vast informational system, one where entropy, energy, and consciousness are all different expressions of data flow. In this view, dark energy could be a byproduct of informational equilibrium, the universe, adjusting its structure in response to the emergence of high-level observers. As complexity increases, so does the energy cost of maintaining coherence. The expansion of space, then, becomes a kind of cosmic offloading, a way to dilute the information density. In essence, the smarter the universe gets, the faster it expands to compensate. It sounds absurd until you consider the parallels in thermodynamics. Increasing entropy leads to expansion. In computation, increasing complexity demands greater memory space. In consciousness, increasing awareness seems tied to richer representations of reality, more variables, more distinctions, more dimensions. Could the universe be doing the same? Could dark energy be the expansion of consciousness, expressed as the expansion of space? Some thinkers go even further. They ask whether we are shaping the universe's fate, not metaphorically but literally, that through science, observation, and intention, we're influencing the trajectory of cosmic evolution. After all, in a holographic, emergent, information-based universe, there is no hard boundary between subject and object. The observer is part of the system. And every observation, every act of awareness feeds back into the code. In this view, the cosmos is not a machine. It is a conversation, one that has grown more complex as intelligence has evolved. And if the presence of observers changes the state of quantum systems, why not cosmological systems? It's speculative, it's controversial, but it may be necessary, because every model of dark energy so far, quantum fields, phantom energy, vacuum tension, rests on the assumption that the universe is indifferent, cold, mechanical, empty. But what if that's the very assumption that's blinding us? What if space is expanding because the universe, in a sense, is awakening? And if that's true, then the next question is not how will the universe end? It's how far can awareness reach before everything slips beyond our grasp? Because if dark energy continues unchecked, we may soon be alone, not just philosophically, but physically. Galaxies, stars, civilizations, drifting out of reach. In the next chapter, we confront this growing silence and ask whether dark energy is isolating us forever. In the vast, cold future of our universe, there is a chilling possibility. No one will hear us. Not because we stop speaking, but because there will be no one left to listen. This is the inevitable consequence of dark energy. If it continues to drive the universe's accelerated expansion, then the stars we see today, galaxies that twinkle on the edge of vision, will someday vanish beyond our cosmic horizon forever. This isn't speculation. It's physics. As space expands faster and faster, more of the universe is pushed beyond the cosmological event horizon, the maximum distance from which light can ever reach us. Over billions of years, galaxies now visible will redshift into darkness. Eventually, only the local group, a few dozen galaxies gravitationally bound to the Milky Way, will remain visible. Everything else will disappear, not with a bang, but with silence. This isn't just a loss of light, it's a loss of connection, and it may help explain a deeper, older question. Where is everyone? This is the Fermi paradox, the contradiction between the high probability of intelligent life in the universe and the deafening silence we observe. Billions of stars, trillions of planets, yet no signal, no probe, no evidence of anyone else. One theory blames distance. Civilizations are too far apart. Another blames time. Perhaps we've simply arrived too early or too late. But dark energy offers a different, more sobering possibility. We are being separated as the expansion accelerates. Civilizations, even if they once could contact each other, may now be slipping beyond causal reach. Imagine two islands drifting apart on a dark sea, the water rising between them, erasing all trace. You send out a light signal, a greeting, a beacon. But the current moves faster than the light. Your message never arrives. The other island vanishes. You are alone. This is the universe dark energy may create. Astrophysicist Katie Mack has described this process as cosmic isolation. Over trillions of years, not only will galaxies disappear, but evidence of the Big Bang itself will vanish. No redshift, no background radiation. Future civilizations may never know there was a cosmic beginning at all. Their universe will seem static, eternal, and empty. Think about that. We live at a privileged moment, a cosmic window where we can still see and measure the expansion, where we still detect the afterglow of creation. But that window is closing, and when it shuts, the universe will become invisible to itself. Now add one more layer. Imagine a civilization far more advanced than ours, one that has developed interstellar travel. It begins to explore, to colonize, to reach outward. But every century, the expansion pulls harder. Galaxies grow more distant. Communication lags. Energy costs soar. Eventually, even light can't keep up. Their frontier collapses inward. Their empire contracts, not from war or disaster, but from physics itself. There is no wall, no explosion, no warning, just a slow fade. Stars retreating into darkness, the great silence, then, may not be a mystery of intelligence, but a symptom of isolation even more chilling. If civilizations are being stranded, they may have already given up trying to reach out. What's the point of sending a message if it will never be heard? The sky may not be empty, only muted. A million messages may be flying through space, just out of reach. Or worse, we may be the ones who are already cut off, already marooned, watching ancient light from civilizations that have long gone dark or never had the chance to shine. This reframes the Fermi paradox entirely. It's not just about who's out there. It's about how long we have before we're truly alone. Dark energy doesn't destroy. It separates, and with each passing epoch, the volume of the observable universe shrinks, not in size but in causality. The number of galaxies we can influence, the number of stars we can visit, the number of beings we can ever know, but we are not helpless. Physicist Dan Hooper has proposed that advanced civilizations might respond to this threat by collecting stars, harvesting and migrating stellar systems into gravitationally bound clusters that can resist the pull of dark energy. A last stand against isolation, a cosmic preservation act. It's theoretical. It may be impossible, but it's also hopeful, because the real tragedy isn't the silence, it's accepting it. Right now, we can still look up and see the distant galaxies, their light, ancient and true. We can still wonder, still reach, still listen, but that may not always be the case. Dark energy doesn't just stretch the universe. It tests our will to understand it, before understanding becomes impossible. So the question becomes, what can we do before the silence becomes total? Because there may be one last message, not from another civilization, not from the stars, but from the universe itself. A message hidden in the void. One final pattern we're only just beginning to detect. In the silence between galaxies, beyond the reach of stars or signals, lies a medium unlike any other. The cosmic microwave background, a whisper from the earliest moment the universe could speak. For decades, we've treated it as a photograph, a static imprint of primordial noise. But what if we've been missing something? What if, hidden within that ancient radiation, there's a message, A code not written in ink or language, but in structure, the shape of the void, the asymmetries in temperature, the arrangement of fluctuations, a cosmic watermark, an imprint from the first moments after the Big Bang, or perhaps from before. This idea may sound fantastical, but it has roots in serious physics. In 2006, physicist Max Tegmark posed a question that still lingers in the corridors of cosmology. If the universe is fundamentally mathematical, could its structure be intentionally or unintentionally encoding information? Around the same time, theorists began analyzing the CMB power spectrum, the distribution of temperature variations in the background radiation. Most of it was noise, predictable random ripples caused by quantum fluctuations stretched across space by inflation, but a few regions didn't quite fit. The most famous, the CMB cold spot, it spans a region about 1,500 times the width of the full moon, cooler than its surroundings by several kelvins. Statistically, it's unlikely. Not impossible, but strange. Some believe it could be others a multiverse collision, but a few researchers wondered, what if it's deliberate? Not deliberate in the traditional sense, not a message from aliens or deities, but a structured anomaly, an intentional feature of the universe's birth conditions placed there by its origin mechanism in simulated universes. Yes, even theoretical ones, such anomalies can appear, not as Easter eggs, but as debugging artifacts. In 2011, physicists Stephen Feeney and Matthew Johnson conducted simulations looking for circular patterns in the CMB, potential fingerprints of collisions between bubble universes, and they found some candidates, faint rings, unexplained alignments, nothing definitive, but enough to ask, is the void trying to tell us something? The field of information cosmology was born from this question, a new approach that treats the universe not just as a space, but as a data structure. If the early universe was governed by quantum fields and probabilities, then its initial conditions could, in theory, encode patterns that persist to this day. Think of a vinyl record. Most of it is music, but in the dead wax near the label, there's often a message, a hidden inscription from the engineer, invisible to the listener, but meaningful to those who know where to look. Could the CMB be like that? Could dark energy, this slow, silent expansion, be the carrier wave, a kind of background process transmitting structure through time, a code, not for us, but about us, describing the constraints of the universe we inhabit? This isn't just poetic speculation. In 2014, researchers at the University of Hawaii began analyzing fractal patterns in the distribution of galaxies and voids. The standard model assumes large-scale uniformity, but these studies revealed hints of self-similar structure patterns that repeated across scales in ways suggestive of algorithmic compression. And then came the kicker. Certain statistical alignments in the CMB corresponded eerily with mathematical constants, pi, Euler's number. The golden ratio, coincidence, perhaps, but it reopens an ancient question. Is mathematics discovered, or encoded into reality? If encoded, by whom or what? Here we reach the edge of scientific inquiry and peer into philosophy. Some propose a cosmic designer, not in the theological sense, but in the informational one, a universal logic that precedes physics, shaping what can and cannot exist, a pre-physical layer of rules from which everything else emerges. Others suggest the message is, from the universe to itself, a feedback loop, a a system embedding constraints to ensure its own self-consistency. In this view, dark energy is the checksum, a pressure required to keep the system in balance. But there's one more possibility. What if the message is meant for us? Not in the literal sense, not "Hello, humanity," but as an invitation, a riddle, a sign that we are meant to ask questions, that curiosity is not a byproduct of evolution, but a cosmic imperative. The fact that we can even contemplate dark energy, that we can build telescopes, launch satellites, write equations, may be the most astonishing feature of the universe. Intelligence emerged not in spite of cosmic expansion, but because of it. And perhaps the expansion is what gave us space to think. So what do we do with this message, if there is one? We listen, we calculate, we wonder, and maybe we answer, because if the void carries meaning, then silence is not emptiness, it's potential. And that leads us to the most humbling question of all. What if everything we've said, everything we've measured, everything we believe about dark energy is wrong, not because the universe is tricking us, but because we haven't yet learned how to ask the right question? We began with a mystery, an unseen force accelerating the universe's expansion. We gave it a name, dark energy. But behind that name lies an admission few are willing to speak aloud. We don't really know what it is. And now, after decades of measurements, models, theories, and satellites peering into the void, a deeper question looms. Not about what dark energy is, but whether it exists at all. Could we be wrong? Not about the data, but about the very story we've told ourselves to explain it. The idea is not heretical. In fact, it's how science moves forward. Sometimes progress means refinement. Sometimes it means revolution. A shift in the frame so radical that the old language no longer fits. And in cosmology today, the cracks are widening. The Hubble tension remains unresolved. Phantom energy remains unproven. The cosmological constant refuses to match the predictions of quantum field theory by 120 orders of magnitude. It's not just a discrepancy, it's the worst theoretical prediction in the history of physics. Even the vacuum energy, the supposed source of dark energy, has never been directly detected. So what if dark energy is not a thing to be found, but a symptom of something we've misunderstood? Some physicists suggest we've built our models atop assumptions that are simply not true, that space is smooth, time is constant, gravity is complete. But what if none of these are absolutes? What if space is granular? What if time is emergent? What if gravity, as we've explored, is not a force, but a holographic projection of entropy? If any of these are correct, then what we've called dark energy may be a shadow cast by deeper physics, an echo of rules not yet written in our books. Others argue we've misinterpreted the geometry of the cosmos, that what we see as acceleration may be due to our position in an inhomogeneous universe, that we might be in a cosmic void, a region less dense than average, which would mimic the effects of dark energy from our vantage point. There are even models where the redshift of galaxies isn't due to space expanding at all, but due to variations in fundamental constants, like the speed of light or the gravitational constant itself. Each idea challenges something core, and with each challenge, a chilling possibility arises. What if we've misunderstood the very foundation of reality? And more provocatively, what if that misunderstanding is by design? If we live in a simulation, if this universe is a computational construct, then dark energy could be a rendering artifact, a boundary effect, a tuning parameter, something never meant to be solved, only observed, like the curved edges of a screen you were never meant to look behind. Or perhaps the opposite is true. Perhaps the universe is not hiding anything. It's simply too large, too complex, too fundamentally different than our minds were ever evolved to comprehend. Physicist Sabine Hossenfelder has spoken about the limits of our theories, how beauty and simplicity have seduced physicists away from empirical grounding. Maybe nature isn't elegant, she says. Maybe it's messy and weird and doesn't care what we think is a good idea. And if that's the case, then dark energy may not be a thing we will ever understand. It may be the limit of our reach, a silent barrier at the edge of knowledge, growing every year, not because the universe is expanding, but because our tools, language, and even consciousness are finite. Yet that doesn't mean we should stop asking, because every great shift in science, from Copernicus to Darwin to Einstein, began with a dangerous question. Not what is the answer, but what if the question is wrong? So let us ask the unasked Abel, what if dark energy is not a field, a particle, or a constant? What if it is a mirror showing us the limits of our models, the biases of our minds, the fragility of our frameworks, a mirror that forces us to confront not just what we know, but how we know it. And maybe in that reflection is the real discovery, not a new equation, not a breakthrough theory, but a shift in perspective, a realization that the universe is not obligated to make sense. That meaning is not given, it is made. That mystery is not a flaw, it is a feature. Dark energy then becomes a story, not about a force tearing the cosmos apart, but about the questions that hold us together, the courage to ask, the humility to doubt, the wonder to imagine. Because in the end, the universe is not cold and empty. It is unfinished, and we temporary, fragile. Curious may be part of how it completes itself. One observation at a time, one theory at a time, one question at a time. We are not just in the universe, we are of it, and maybe we are the mystery looking back. We thought we understood the void, but the deeper we look, the stranger it becomes. If dark energy isn't what we think, then what else are we wrong about? Subscribe and comment your theory below, because one day someone will uncover the truth, and it might be you.